Now you can hear me and now you can see the screen. Okay, welcome back to the African Plants Georeferencing Train the Trainers Workshop. This is Module 3. I'm glad you've all survived this far. Today, we're going to get deep into the actual processes of georeferencing. So what I call the fun stuff. There are two modules today. They're very much related to each other and they'll be somewhat mixed. We believe that what I'll do is half of this point radius method presentation, and then there's a natural break. That should be somewhere between 40 minutes and an hour from now. Then we'll take a 10-minute breather, a break, because it's a lot to digest. And we'll come back and finish the point radius method presentation and go into the georeferencing calculator, which is very little presentation and very much a demonstration. So that's the plan for today. So I'll get going right now on point radius method. The method itself was first published in the International Journal of Geographical Information Science and came out of the methods that were developed for a project that was very much like this one, a large collaborative georeferencing project. And at that time, there were no methods, no rules about how to georeference. So part of our project was to develop those rules, and those rules became this paper. Subsequently, no, I'll get to the subsequently. This is just a quick reminder. Paula gave a presentation on georeferencing methods and pointed out the benefits and drawbacks of several methods. And one of them was the point radius method, which we said at the time was a good balance between being efficient and capturing the georeferences in a largely useful way. So just to remind you quick, it's a single pair of coordinates with a distance or radius from that set of coordinates that includes the entire location and all of its possible uncertainties. And those uncertainties are represented in a single dimension, the radius. So here are 4 examples of what a point radius georeference would look like for 4 different geographic feature only locations. So the first one is described as Lake Magadi, and you can see the point in the center of the lake and a circle that contains all of the lake, plus some extra stuff around it. In the center top is another type of feature, one with a concavity in it, a hole basically, and that's the Ban Hin National Park. Same kind of thing. We have a circle that touches the outermost points of the extent of the place and a radius that describes how big that has to be from the center that is selected. In the center on the bottom, yet another feature, this time a linear feature or a path, the Zambezi River, where again, the point is somewhere on the river and the point radius covers all the possible extent of the river, no matter what its shape is. And then finally, at the right, a point radius representation of the country of Benin. So to cap off what it is, we talked about it as being a method. Now, more specifically, this is what we're going to try to do when we execute the point radius method. So it's a series of practices based on the classification of types of localities. And we gave an entire presentation on locality types. That was to introduce you to what you need to know when you begin this method and enter into this process. So the first thing you do is to locate a point of reference. That is where you're going to start. If it's a geographic feature only, then that point of reference is actually going to be the center of the point radius. But sometimes, especially when there's an offset, like a distance at some direction, That point of reference is going to be where you start, but it's not going to be the same as the point where you end. That will be somewhere at an offset. Then finally, secondly, we'll define the uncertainty that's due specifically to the entity extents. That means we're going to try to find the extent of the feature, that is what's inside it, what's outside it, where's the boundary, and that size is going to contribute to the uncertainty, the final uncertainty of the georeference itself. Sometimes it's the biggest contribution, sometimes not. Depends on how big that reference entity is. Then we need to identify all of the relevant sources of uncertainty. What other factors will come into play to contribute to that radius? We've seen these 4 examples just now of point radiuses for geographic features only. Well, those don't have a lot of other uncertainties. They don't have offset precision uncertainties. They don't have distance uncertainties, directions uncertainties. They're just the size of the place, plus a few other things, smaller things. Then the last step is to perform calculations to find the final coordinates in case that they're different from the original, that we actually need to move from that center that we started with, and the final uncertainty that puts together all of those sources of uncertainty. So this presentation is going to be how to do that. So since the point radius method paper, 3 other documents have been produced. These 3 versions all through the support of GBIF. The first one, the Georeferencing Best Practices, was first published in 2006 and was meant to provide the background theory behind why the point radius method is the way it is. All the things that contribute to uncertainty, why we would describe them the way we do, etc. Then the Georeferencing Quick Reference Guide, again, was a rewrite, but it was a rewrite of something that was only in the form of a spreadsheet, basically a simple list of the kinds of locations that you might encounter and some simple instructions about what to do about it when you do encounter them. This version, this Georeferencing Quick Reference Guide itself, is an in-depth set of recipes of exactly how to do point radius georeferencing for all the locality types that you might encounter. And the final document in the series is a full manual for the Georeferencing Calculator, which we'll see is the tool of choice when manually georeferencing. Okay, so the point radius method, we identify 7 distinct steps to execute it. The first is to take all of the location information that you have and separate it into its parts. So sometimes this is already done for you. For example, we have all those higher geographic fields, country, state, county, municipality, etc. But then we also have the location field, or maybe it's only in verbatim location or verbatim locality. We still need to separate that information out. And we'll talk about that when we get into the second step. But first of all, what do we mean by separate the location information into its parts? So here is an example of a location that has 3 parts. If this were coming to you from a spreadsheet or a database, then Tanzania, the far right part of the description, would be in the country field. And Kagera would be in the first administrative level. It's a region in the extreme northwest of Tanzania. And so that would be in the state province field. And then the part at the left, you might expect to be in the locality or verbatim locality field. And that's the most specific part of this locality. Okay. So that's what we mean by dividing it up into its separate parts. So then once we have those parts, we need to identify which of them is the most specific, because usually that's the only one we really need to do the georeference. Sometimes no, sometimes we need the other ones, either to find out among many possible candidates for the locality or the feature in the locality, and sometimes to restrict what's in the most specific part of the locality to something that's on one side of a board or another, for example. So let's remember that the localities are in these four basic categories of geographic features only, of offsets, they include a distance somehow, or a direction somehow, coordinates, and difficult localities. So these, within each of those larger categories are subcategories that are more specific. So the second step, classifying the most specific part of the locality. In red on this slide, we've identified 4 kilometers southeast of Ikusa Island as being the most specific part. If we look on a map, we find Kagera is a fairly big place, and it includes the island. So the island part is the most specific. And that specific part is the locality type distance at a heading. It's got 4 kilometers, that's our distance. And it's got southeast, that's our heading. Okay, so now we've classified the most specific part of the locality. The next thing is going to be to define the extents of the features that come into play, which of course means we need to identify what the feature is as well to find its extent. So in this case, our locality type was distance at a heading that's from some feature, and the feature that it's from is Ikusa Island. So we've identified what the feature is. Now we have to figure out what are its extents. So we go to a map, and either specifically manually we draw the polygon around the island, or we use our measuring tools on a map, or we do things just by estimation. So I'll show you how we want to do this to do it rigorously. In red is the feature boundary, the outside of the island itself, and we can see the island is kind of a concave shape. And so we're going to have an interesting description of the island when it comes to a point radius. So next step will be to find the centers and radials of the entities. Our entity is the island, the feature in the description. So let's go find its center, remembering that what we're after is the corrected center. This is going to be important, especially in this case where our island is concave. There's a hole in it, and the regular center would probably fall in the water rather than on the island. So the reminder is that this corrected center is a point that's within the feature extent or on its border, and that point helps to minimize the geographic radial. Okay, so what's the geographic radial? The geographic radial is the distance from the corrected center of a feature to the farthest point on the boundary of that feature. So we need to see this visually. There are different cases and methods to find the center and radial depending on what the feature looks like, what's its basic geometry. So we're going to divide this up into several cases. The first one is the case of a linear feature. It's simple. It's a strip of road or part of a river, or maybe it's an airline landing strip, things like that, things that are basically composed of lines. First thing we do is we find the midpoint, in this case labeled as A, of the segment between the two most distant points of the geometry. Here the geometry is the line segment. And on the diagram, it's the thick line, the one that's got dots all the way around it. So we find the midpoint. That should be easy. We measure the whole thing, and we find halfway from one end to the other, and hopefully it falls right in the middle of and on the feature itself. So that's the case here with A. The second step is if that midpoint falls on or in the geometry, and no other point in the geometry is further than the 2 points on the chosen segment, then the midpoint is already the corrected center. So we chose A as being the halfway between the two ends, and it's on the line. So it's already the corrected center. And then the radial would be the distance from there to either end of the line segment. So that's a simple case. Now we get into a little bit more, this is not more difficult or in any way, it's actually conceptually exactly the same, but the shape is different. I have some sound on. Can we mute the microphones there? Okay, so in this case, our feature is a convex feature. And in this case, it's one that's obviously elongated. So it's longer in one dimension than it is in the other. So up, down, it's longer than it is from side to side. So again, exactly the same. Find the midpoint, but this time of the segment or the line between the most distant points on the geometry. So if you look at that shape and try to figure out which 2 points are the furthest from each other in the whole shape, it's the ones that have been connected already. So the ones with the red line that goes through the point A, the solid line. Okay, so now we test, is the midpoint in the geometry or on its boundary? And is any other point in the geometry further than the 2 points on the chosen segment? The answer is no. So it already falls on the midpoint, and it is the corrected center. And therefore, our geographic radial is the distance from that center to the farthest point, which would be either the one on the top or the bottom. They're equal distances because of how we measured it. And that's the radial. So very similar to the first one, but now we're getting into shapes that aren't just lines or line segments. Now, suppose we have a convex feature and it's not obviously elongated. So it's kind of as wide as it is long. So in this case, we're still going to try to find the midpoint A of a segment between the 2 most distant points on the geometry. This is always our starting point. In this case, we do it with the line going, the solid line going through A from top to bottom. And then we draw a circle with a center on that midpoint A and the diameter that extends to the 2 extremes of the segment. So the point furthest to the top and the point furthest to the bottom. We want that to be our circle for now. So we do that, and we see that the circle doesn't cover the entire shape. So that's not going to be possible to be our final center. So we take step 2. If any point on the geometry falls outside of the circle, we see that it does. On the right-hand side, there's a whole triangle that falls outside of the circle. Then we need to move the center, or our whole circle indeed, so that the furthest 3 vertices, specifically 3, of the geometry are equally distant from the new circle. So we haven't changed the size of the circle. We're just sliding it to the left from point A to point B. And by doing that, we get a new circle, the same size as the original dotted circle, this one in a solid line, and it's moved to the left. And if you look at all the borders, all the points that stick out the outside of that solid circle, you can see that they stick out the same distance in all 3 cases. So this has taken care of finding the center, the corrected center of this geometry. But we don't have the radius yet because there's still more outside. We need to adjust our radial from point B, make our circle a bit bigger, and have it cover all 3 outside points. So that ends up being our same point B. We haven't changed our center, and the radial C to cover the entire geometry. So you might be wondering why 3 vertices? Geometrically, 3 is the minimum number of vertices needed in order to draw a circle that completely encompasses a shape. Sometimes there might be more than 3 vertices that actually touch the circle when you're done, but only 3 are needed. That's just a geometrical property. So that's the case of a convex feature that's not obviously elongated. Now we go into a concave feature. So that means there's some kind of indent somewhere. And in this case, you can see the indent in the lower right of the geometry of the feature near the point A. It sticks in. We're going to use the same process. So first, we find the midpoint A of the segment between the most distant points on the geometry. In this case, the upper right point to the lower left point is the longest possible distance on the geometry. And we're going to draw a circle around that point. So we get the dotted circle in the middle figure centered on the point A. Now, we do a test. If any point in the geometry falls outside that circle, and it does, again, this triangle in the upper left sticks outside of our dotted circle, that part right there, then we need to move the center. We need to move it in that direction so that, again, when we finish our circle, the three vertices of the geometry that are equally distant from the new circle is achieved. So from A, we move the circle to B. We end up with the same size circle, solid in this case again, that just barely sticks inside of all three of the most distant vertices of the shape. And then again, same thing as in the last case, we're going to make the shape, or the circle, sorry, a little bit larger to make sure that the entire shape is inside. Just a tiny adjustment in this case. And then we end up with our radial C. So very similar to the previous case, it didn't actually matter too much that it was concave because the center was within the geometry. Process is the same. Now, we get into a concave feature. It's got an indent. In this case, the center that we find from the first step is not within the geometry nor on its border. So here we have to do something different slightly. We're going to start with the same process. We find the midpoint A of the segment between the most distant points on the geometry. Again, exactly the same as the previous one, the upper left and lower, upper right and lower left, sorry. And we draw that circle. Now, we're going to try to adjust that circle in the same way as we did before. When we do, we move that circle so that the center falls on or within the boundary of the geometry. So if we stop too soon, we're still in this void that's not part of the geometry. We need to go further. We need to go further so we actually put the new center on the border, not outside it. That's the rule of a corrected center. So then we try to do that while meanwhile maintaining the distances of the most distant vertices being equal. So it's very similar to the previous case, but we need to make sure that we adjust this point B so it's actually on the boundary or inside. Once we've done that, again, we're just going to increase the radius enough so that the most distant point from our new corrected center C is contained within the geometry or on the border of the geometry. So hopefully that's fairly clear. The difference being you might have to adjust your center B just a little further to get onto the boundary. Okay, now we get into things that are composed of polylines. They're curves and line segments and things like that. And in this case, just like in the previous example, the center does not fall on the boundary. It's going to be somewhere off of the boundary. Same process, but different graphic. Again, we find the midpoint of the most distant points. That's A and the circle around it. And we can see that that circle doesn't cover the entire feature. Well, let's just say it's a river. Doesn't cover the entire river. So we know we have to move the point A somewhere in the direction to cover that edge. So we begin to move it, and we have to move it far enough so that it's this new center of the new circle is on the river. So we end up finding point B. So in point B, we're on the river. We've satisfied the corrected center criterion that it has to be on the boundary or inside the feature. And we have our circle. We haven't changed its size. And it looks from at this scale like it actually is sufficient to cover the feature. But when we look in detail, it will not be exactly covering these 2 points. We'll not be able to satisfy all 3 extreme points just by moving that original circle. So we'll have to adjust. And that's this third diagram where C here is the same as B there. We haven't moved that center, but we had to expand the circle a little bit to make sure that it caught this lower part of the river. So that then it will be our corrected center and our new radial D for this kind of feature. Great. So now let's go back to the example that we began with, which was Ikusu Island, which formed part of a larger locality type that was a distance at a heading from a feature. So this is our feature for the distance at a heading feature. Let's classify this. This is case 5 from the previous slides. It's a concave feature. It's got an indent, and the center is outside of the geometry. To convince you of that, let's take the midpoint of the furthest 2 points in the geometry. So I did this measurement very carefully on Google Maps and in this slide. And the line segment here, the solid line that goes through A, is the longest one, but just barely. You might suspect that this point down here at the very bottom is further away from the one at the top than this one. But if you measure it, it's just a tiny bit less. So this ends up being the segment that we need to start with, and we find the center is completely off the island. Okay, I'm going to take a pause because there's a question on the chat, and I think I need to address that.
So in the chat, there is a question that says, is the movement of the new center always towards the most distant point?
Yes. The answer is that it's more or less in that direction. It might not be directly in that direction because you might not get to the boundary the fastest that way, but it has to cover the extremes of the geometry in that direction. So that's a good guess about the direction to start going. Go directly that way. And at some point, you're going to get either onto the boundary, or you're going to get to a point where you realize if you go any further, you're going to actually start going further away from the boundary. So the answer to that question is yes. And it's a good question. Every time you do this method, you're going to encounter that. Okay, so we've seen this. We've got a nice line segment. We've got a center that's not on our geometry. What do? We translate our circle, same size, but with a new center that tries to make these distances here. If you have to watch my cursor. The distance from here to here, that extreme, the same as the distance from here to here. So we're trying to keep the distances outside the circle here and here being the same. If we do that, then we've found the corrected center. It's on the border, and it is going to end up minimizing the size of that circle. So that's what this slide is saying. We're not done because our circle is still too small. So we take the final step, which is we increase the radius from our new corrected center B so that our circle just touches the outermost edges of the island. And that is our new corrected center and geographic radial for Ikusu Island. And we're going to use the results of that to begin the georeferencing process for our distance at a heading locality type. Remember, all this was just to try to find the size of and center of the island. our starting place and our starting size. So there's a note at the bottom of this slide that says, remember, the uncorrected radial, the one we began with, is always, but always, less than or equal to the corrected radial. We will always have to expand our radius to cover the edges. Okay, so that was great. That's finding the centers and radials of the entities, and that's one of the most important parts of this georeferencing process. You'll have to do it every time that you have a feature that you need to find the size and radius of. The next thing is going to be to identify all the other sources of uncertainty that will have to come into play. So let's just have a look at that. Remember, we've seen sources of uncertainty in previous presentations, and they basically amount to these. There is imprecision in how the distance is represented. So if I say 4 kilometers, that's not the same precision as 4.1 kilometers. 4.1 kilometers is more precise in its distance, and it means that the contribution to uncertainty from distance imprecision is going to be less. The same kind of thing applies for directions. Some directions are more specific than others. For example, north is basically anything between northeast and northwest. It's a big angle of 90 degrees. But if we say north-northeast, we're demonstrating a more refined understanding of the direction. So now north-northeast is a smaller angle. We know it's between north and east, which is, sorry, is between north-northeast and east-northeast. So the angle is now 45 degrees, it's diminished, and the imprecision is less. And if we had a heading that happened to be at a degree, a single degree, then it's very refined. Then there are other uncertainties from the sources themselves. Sometimes we won't know what the datum is. This happens a lot when we get coordinates in our description. It just has coordinates and doesn't tell us the datum. Not knowing that datum contributes a lot to the uncertainty. Most of the time when we're doing georeferencing, such as the example we're working on now, we don't have any coordinates to begin with. So we're going to use a source like Google Maps or Google Earth, and that does have a known datum. So the uncertainty from unknown datum goes away entirely, which is a beautiful thing. There is also a source of uncertainty from the coordinates. Again, if we begin with coordinates, then we're stuck with the precision that we've been given them in. So 2 decimal places of a decimal latitude is much less precise than 6 decimal places in the decimal latitude. And so the earlier one with 2 decimal places is contributing more imprecision. It's going to end up making our uncertainty much greater. Then there are issues of errors on the maps we use. This is true with paper maps. This is also true with online maps, including Google Maps and Google Earth. Happily, those are fairly small and they are known and they are incorporated in the tools in the georeferencing calculator, so that you don't have to figure out what those are. We already know. But then there's the measurement error. So this comes up whenever you engage in a measurement on a map. In a paper map, it's your ability to define the distance between 2 points. For example, how far might you slide the ruler between one attempt and another? That's your measurement error. The same thing happens on online tools like Google Earth or Google Maps, where you're using a little tool to measure distances. The tool is great. The tool's measuring the right distance, but you may not be so great. You may not be actually pinpointing the beginning or end points precisely, depending on, especially on the zoom of the map. if you're zoomed way out and you're looking at a big area and you draw two endpoints, those two endpoints are going to be off from what they really should be if you zoomed all the way in. So that part that's off is your measurement error, and that comes into play as well. Finally, there's a source of error from GPSs. So if we know that the coordinates that we received are from a GPS, but the accuracy of the GPS at the time was not recorded, then we need to provide some default possible errors based on the conditions of the GPS in the place and time that the thing was taken, which weren't recorded. So we need to provide a conservative estimate of what that is, and that varies. Okay, so those are our sources of uncertainty. We've identified them. We haven't done anything about them for the georeference because we're going to use a georeferencing calculator to do all that for us. That's the happy news. We've got a tool. So the sixth step is to actually calculate the final center, which might not be the same as the one that we figured out already, and the final uncertainty. Why might it not be the same final center as the original? Take our example. Our island is just the feature that's mentioned. The final place is 4 kilometers southeast of it. So the final center is going to be offset from the one that we've found so far. So these calculations all depend on the locality type. Different kinds of uncertainties come into play. For example, you wouldn't have any uncertainty due to the direction if the locality type doesn't have a direction in it. Same thing for distance. If it doesn't have an offset, some distance in it, there's not going to be an uncertainty due to the distance. So all these locality types are going to have different values that come into play to contribute to the final uncertainty. And to do this for the point radius method, the georeferencing calculator is tailor-made to do exactly this. And the georeferencing calculator looks like this. We're going to go into it in detail in just a moment. But here, what I wanted to do was to point out that we have two documents that are specifically aligned with using the georeferencing calculator to do point radius georeferencing. The first one I mentioned already was the calculator manual. The manual describes detailed from step one, opening the calculator or even getting it open on your browser, to how to fill in all of these fields for different types of localities. So it's very detailed, and you're going to find that manual to be your friend when you start to use the calculator. The companion document is the Georeferencing Quick Reference Guide, which tells you how to go about interpreting the shapes and how to do the corrected centers and radials, just as we've seen already in this presentation. Those are examples taken from the Georeferencing Quick Reference Guide, or were adapted from it. Those two documents are going to be essential. They're going to be at your side. This calculator is going to be at your side when we do our georeferencing. So the final center and radial calculations are going to end up giving you results that will map directly into Darwin Core. The final coordinates, we're going to go into the fields decimal latitude and decimal longitude, and they will be transformed into that format for you, even if the original was different from that. Then the coordinate reference system is something that you're going to have to pick from a list in the calculator, and that will end up in the geodetic datum field. And then the final uncertainty that the calculator gives back, the net one that puts all the sources of the uncertainty together in the correct way, none of which is simple. There's some complicated math in some of it. Will go into the coordinate uncertainty in meters field. So you can see we're populating Darwin Core directly with the minimum viable georeference, these 4 fields. So the last step is going to be to document the georeferencing process. We have said this over and over. We're going to hit the nail again and again and again, which is to say that you need to provide the information that helps someone else assess your georeference to the point where they can reproduce it. They need to be able to use your protocol, your sources, and your remarks to come up with the same answer and understand why you came up with that answer. So that's what the documentation is about. And it goes into these three Darwin core fields directly: georeference protocol, georeference sources, that would be your maps, etc. The protocol would be your georeferencing quick reference guide, assuming that that's what you're using. And then any rationale, criteria, decisions, exceptions that you had to make to the protocol are going to go into georeference remarks. So we're filling up Darwin core completely with everything that makes a best practice georeference. So we're going to take a break here, unless there are questions to answer right now, and we'll go into some steps for specific locality types. First, it's quite involved and long. And at the end of that, we're going to go to the georeferencing calculator and look at how that functions. So I'm going to stop the screen share here, see how we're doing in terms of questions. Do we have any open questions? The last one I see is one that I've already answered about moving the new center toward the most distant point. If there are no other questions, I'm going to call now for a 10-minute break. We'll come back basically at, well, the hours are different, but 10 minutes from now. Okay. Give it a few seconds for any other question. Was that a question? I heard something. Okay, so 10 minutes. I'll come back and we'll start with the second half of that presentation on the point radius method and get into some specifics for different locality types. So we'll see you soon. Okay, we're back. Hopefully you can hear me. I'm going to start right in, sharing the screen and continuing our point radius method presentation. Okay, so you should be able to see steps for specific locality types on the screen now. Let's get right into it. So I want to say something about all the slides that are going to follow before we go through them, and it will simplify things for your brain. So the basic layout for each of these coming slides is going to be something like this, where the major locality type is given at the top. The minor locality type, or the specific locality type inside of that, is given just underneath it. Then there's going to be a set of calculation parameters. These are all of the parts of the georeferencing calculator that are going to come into play, the things that you will need to enter something for in order to make the calculation. At the right will always be an image that's a representation of the very specific locality type that we're talking about. And sometimes underneath, there are going to be some comments. So the reason I wanted to point all of this out is that these calculation parameters here, once we understand them from this first slide, they're not going to change for very, very many slides until we get out of the geographic features only. So let's understand these calculation parameters, and after that, we can just realize that they're the same every time, and I will alert you when there's a change, when there's some other calculation parameter that needs to be taken into account. So We're talking about a geographic feature only. So here we've got an extent with this boundary for a geographic feature only. And this one has a very obvious spatial extent. We're able to draw that border very clearly and be confident that that's where it ends. So the calculation parameters, the things that are going to contribute to the calculation are knowing where the coordinates come from. Are they from the locality description? Are they from Google Maps? Are they from a gazetteer? Are they from a printed map? If so, what scale, etc.? That's what coordinate source is for. The coordinate format is going to be the set of possibilities that we might put into the verbatim coordinate system field in Darwin Core. So that will be either decimal degrees or degrees decimal minutes or degrees minute seconds. So we'll have to say what coordinate format our coordinates are coming in from. So we grab these from Google Maps, then it's going to be decimal degrees. And we'll have to say so, because otherwise we won't be able to enter the coordinates in the right format. Then we're going to get the coordinates of the corrected center using the processes that we talked about in the previous part of the presentation. So depending on the locality type, we figure out our corrected center. We will need to enter the datum. So either we know the datum and we select it from a list, or we don't know the datum and we select the value not recorded from the list in the georeferencing calculator. And that's absolutely essential. We will know the datum if we use Google Maps or Google Earth. We won't know the datum necessarily if we just get coordinates. The coordinate precision is going to be important, and we talked about that a little bit already. If we get our coordinates from a locality description and written down, we need to figure out what that precision is and enter that in the calculator. If we're getting it from Google Maps or Google Earth, and when we copy those coordinates as decimal degrees into the calculator, if we copy the entire thing, the coordinate precision is going to be exact. If we get the coordinates from something like a gazetteer, and it gives us 4 decimal places of decimal latitude or decimal longitude, we'll have to select that that's a 0.0001 coordinate precision for the calculator. The radial is B in this diagram, in our figure. We have already figured that out using the processes that we talked about. We'll need to enter our radial into the calculator. Along with that, we're going to have to use the units of all of our measurements and our radial and set that in the calculator. This is interesting because remember that the output from the calculator or from the georeferencing process in general is going to be a coordinate uncertainty in meters. The net final uncertainty is going to be in meters, but our locality description isn't necessarily going to be in meters, and we need to put the description as it was given. So remember our example from the first part of the presentation, which was 4 kilometers southeast of Ikusu Island. In that description, our units for distance were kilometers. We need to maintain that. We need to be able to put in our offset as kilometers. We need to put in our radial as kilometers. We need to do everything as kilometers, because if we don't, then the precisions will not be calculated correctly. So we'll see that again later. Then finally comes the measurement error. And remember, this was your ability to distinguish between 2 points on a map when you do a measurement. And that's a number that you're going to have to find out empirically by testing yourself. And we'll see how that could work. Okay, so that's how all the following slides are going to look. Remember that these calculation parameters are going to be exactly the same, so I won't need to explain them every time until we get to some new ones. Okay, so the second specific geographic feature only Locality type is one where the boundary is not so clear, a diffuse boundary. And our canonical example for this is a mountain. So on the right, we have an image and we have a dotted black line that is an interpretation of what is the mountain. So inside of the dotted black line is what we think the mountain is, and outside of the dotted black line is something else. It's some other mountain in this case. So how do we decide that? We have to make some judgment calls because it's not entirely clear. It's fairly subjective. So what we do is we look around all of the edges. We know where the middle of the mountain is, the part that has the label on it, somewhere, or near to the point A on that figure. Point A is definitely on the mountain. Once we start going down the hillsides, so at some point, we're not going to be on the mountain anymore. So if you understand how these maps work, this is a topographic map, and it's showing lines of elevation. So the ones nearest to the point A are the ones that are highest. And as you go away from point A, they're getting lower and lower and lower until, for example, on the two sides of the dotted black border here, you can see that the lines are not connected. The line on the top here is completely enclosing the mountain, and the one on the bottom is not completely enclosed, is not connected at all. What that means when you read a map like this is we reached the bottom here, and now we're starting to go back up again. So that line through that valley seems like a fairly reasonable place to draw a boundary. It's this mountain on this side, and then we go up on this mountain on that side. And we can do that all the way around the mountain. Here we have the same thing. We reach a minimum, and then it starts going up again in that direction. Here, through here, we reach a minimum, and it starts going up again on that direction. Same here. So by drawing this dotted line here, what we've said is we're going to go down the mountain as far as we can until we have to go up again to get to something else. That's how that interpretation of the mountain was made. It's not always that easy because you don't always have mountains around to tell you where to stop. Sometimes there might be a different thing over here, a different feature, like a town, or it may just flatten out and you say, okay, once I get to the bottom and it's not going down anymore or up anymore, I'll put my boundary there. Like I said, these are subjective, they're diffuse. And so what you do is you try to make it halfway to the next thing that isn't your feature, and you draw your boundary there. The important thing is, sorry, let me go back. The important thing is to document how you made those choices. And that's always the case. Okay, so on to the next geographic feature only type. So this one has no apparent boundary whatsoever. You will find an example of this on a printed map, for example, where there's a symbol and the symbol has a name by it. So, for example, this symbol might be the symbol for a spring where the water comes out of the ground, or an oasis, something like that. But the map doesn't show how big it is. It just shows more or less where it is. So what do we do in a case like this? We've only got a feature that's identifiable by a marker on a map or coordinates in a gazetteer. We have no idea how big it is. What we need to do in those cases is apply a rule for some predetermined radial that's based on the feature type. What do I mean by that? So let's take these examples. That we might have a table of radials of how big to make a feature when we find it and are unable to see its boundaries. So here are some examples. The example I just showed was supposed to have been a spring. So in that case, what we would use is 3 meters. Say, okay, a spring is 3 meters wide. We need to document that, of course, but at least it gives us a rule, and we can be consistent and use the same sizes for the same things over and over. And you can see this list has several different categories. The list could be long, very long indeed, one for every kind of feature type. It includes things like small features, like how wide are highways, some specific kinds of administrative divisions that are smaller than municipalities, and even grid systems. Like, okay, if I have UTM coordinates, how big do I make the feature? And that depends on how much precision the UTM is given to you in, and varies by factors of 10 as we go up. And then there's also how big is a grid for a 1/4 degree grid system. And that varies with latitude. So be careful about that one. So that's what we do in the case of a geographic feature only that has no apparent boundary. We have to come up with one, and we have to say why we said so. Next, we get to just a specific example of a feature with an obvious extent, but this case it's on a street. It's an address. So Google Maps, for example, can show you exactly where the address is, and you are able to draw the boundaries around it normally. And so it's just like our other feature type. The other case is that you have an idea of where the address is, you know what block it's on, or what section of the street it's on. So you can put boundaries on the two sides of the street, but we can't actually say where within the street it is. Okay, I'm going to take a pause because I think there's a question. Let me see if I can see what that question is. Okay, pausing.
So there is a question that says about parameter calculations. Are there any special tools we should use to estimate the center of an object on satellite images other than shapefiles? Shapefiles are not an issue when using GIS applications.
Yeah, the answer to that is yes. We're going to use and describe in detail 3 different tools and what each one is good for. So some of the measuring we can do with Google Maps. There's a measurement tool built into Google Maps. Paula's favorite, and you'll see this when she talks about Google Earth, has a lot more capabilities for drawing. You can draw circles and lines and polylines and polygons, and you can put lots of different ones on the map and do all these measurements and find areas, etc. So that's a very good tool. And then we'll talk also about a new tool that has just been developed, and you'll be the first ones to use it for real, and that's called GeoPick. And GeoPick is a combination of, let's say, Google Maps, an OpenStreetMap, and the Georeferencing Calculator for the geographic only type locality types. And so that third example of GeoPick is going to allow you to draw polygons as well, and then do calculations directly as if it was the georeferencing calculator. So it's a nice combination of tools. If you have GIS, you can use that too, as you mentioned. We're only going to talk about those 3 tools in particular, but there can be others as well. And if you have a particular tool you already know and are familiar with, please share that and we can mention it to others as well. That okay? Should I go back to the presentation? I see another question. In the literature, we can see, for example, resolution 2.5 minutes or 5 kilometers or 30 arc seconds, 1 kilometer by 1 kilometer. I want to know if it is the radius method. Okay, this one's tricky because if you look at these examples, just take the first one, for example, it says resolution 2.5 minutes. And then it says 5 kilometers. That 5 kilometers is an estimate, probably based on the distance at the equator. If you think about it, 2.5 minutes, that's part of a degree, changes as you go north or south. So 2.5 minutes is a very poor way of describing distances on maps because it changes. The same with 30 arc seconds. Okay, it says it's a kilometer by a kilometer because that's what it's close to when you're at the equator. As soon as you move away from the equator, 30 arc seconds is not a kilometer by a kilometer. It's not even a square. So again, these kinds of measures that are based on degrees are very poor descriptors of size. And what we want to do is to get to the actual size, the kilometers in the situation that is. Those sizes as kilometers or as meters are definitely used in the point radius method, but those resolutions in degrees are not. That's what I'm answering. Yeah, I've answered these two questions that have come up. Okay. So now a third question is the area of extent for a mountain a circle? No, not necessarily. That would only be if the mountain was circular, like a nice volcano that makes a perfectly circular cone, then the extent would be circular. But that's seldom the case for a mountain. Often the mountain is shaped differently. So the extent would be different from a circle, and you'd have to draw that to get the final shape. These are all good questions. Are there any others just now? Is there any way to find the datum based on the GPS device used? Fantastic question. The answer is, if you don't have the GPS in your hand, no. If you have the GPS in your hand, yes. You can look at the configuration of the GPS and find out what it is. If you don't have the GPS in your hand, your only real hope of knowing what the datum was on the GPS at that time is to have more of a description than just the coordinates that the GPS gave. So what I mean is you have the coordinates from the GPS and you have a description of the place, and the place is so specific that you can tell if the point falls on that same locality because of the textual description. And if so, you could say, yes, look, the point matches the description if I use WGS84. Therefore, I'm going to say that the underlying datum for the GPS for this measurement was WGS84. If you don't have that very specific situation with the GPS coordinates and a very specific place to confirm a datum assumption on, you can't say what datum the GPS was in. This is an interesting point. You might think, well, GPSs have saved the world because they're very precise descriptions and places on the Earth. We've removed all the uncertainty due to coordinates, etc. Remove the datum from that. I'm sorry, you just lost 5 kilometers of certainty. And it's very sad when people don't know that and don't record the datum with the coordinates. They say, from GPS. Great, thank you. That doesn't tell me anything. Good questions. Okay, I'm going to go back to the presentation. And if we get more questions, let's accumulate them for a bit and I'll get back to them. Okay, so please confirm that you can see the screen. We were with, obvious postal addresses. And I think we've finished this one. It's just a specific case of a geographic feature only with a well-defined boundary. We're talking about this one. Here it's similar, but we don't know where on the block it was. So what we need to do is define the places that it might be. It could be either side of the street, and it could be anywhere within the block up to halfway across the other block. So we're able to draw, figure out where the center of the street was. It's on this street and it's in this block. So those are the boundaries on the street. And it could be anywhere within the interior of the block up to halfway through the block. So we're drawing a box that contains all of that area, put our corrected center right at the center of the box, and our diagonal is our geographic radial for that one. So that one's pretty straightforward as well. Then we get into situations that are also similar, but they're not with a street address. There's something like a ranch or some other property. It could be a school, etc. Here, we try to find the exact boundaries again around the feature, such as here, and we do the same old thing. We find a corrected center. Hopefully, if it's concave, the center falls within the boundary. We don't have to do any corrections, and our radial is just to the farthest corner. So that's normal. But then we get properties without obvious boundaries. Here we have two situations. One situation is we know, for example, in the darkened part here, we know that this part is part of the property. But we suspect that all of this other stuff might be part of the property as well. We have some information that suggests that it might be anywhere in this. So our final georeference needs to contain all of this suspicious part, but we can constrain our center to be on the border of the part that we know for sure. So that's what this diagram is showing. What we want to do for this then is delimit the external boundary, and that, because it's not obvious, we'd have to use the neighboring features and say, okay, this is halfway between the known thing and some other known thing in this direction. So we draw our boundary halfway there. Similar situation in this direction, similar situation in this direction. There's something that begins right here already. So that borders very close to this very well-known part of the place, etc. So that's how we draw our exterior boundary. Then we also draw a shape for the well-known interior part. And we use our exterior part as the extent to try to find our corrected center on. The center of the outer boundary would be C. We adjust it to be the closest point to that on the known property and make that be our corrected center, and then draw a radial to the outside of the suspected property. So again, this is subjective, just like the not obvious boundaries on a mountain. Okay, now we're still in geographic features only, but we're getting into different kinds of shapes. They're not geometries like the polygons. Instead, they're polylines or paths. So the calculation parameters still haven't changed. These are all exactly the same as in every slide before. Now, what we want to do is, if we can, we want to treat this path as a shape. What does that mean? That means, suppose that's a river, and suppose it's a big river. It means that river has width. It might be 20, even 100 meters across. So if that's the case, and we're able to see that, then we want to treat the river in its full extent, not just the line down the middle of it. We want to do that if possible. If we can't, if the width of the path is not evident, then what we want to use is a buffer. A buffer means that we want to set a constant distance from either side of the line that we're given that would be part of the feature. So suppose we're just given this line. We have no idea how wide the river really is. We can't see it on a map, and it's not shown in our figure. Then what we do is we say, okay, based on my best information, this is a fairly small river, and we're going to give it a width of 20 meters. And so that's the buffer. The buffer is that 20 meters, 10 meters to either side of the line that represents the river. Okay, take note that the scale, which in the case of something like Google Maps or Google Earth is reflected in your zoom level. That's how much can you see at once? How close is your image? The scale and the type of representation of the map can reduce the complexities of the real world feature. So, for example, in our drawing here, looks like it's fairly detailed. We've got little curves all over the place, et cetera, et cetera. On a different map, this might be average. There might be just a line segment there, a line segment there, a line segment there, a line segment there. And so the complexity is reduced. And when the complexity is reduced, that means the measurements are affected. It means you're not actually following all these little changes in the river. You're actually simplifying it and making every distance less. The same thing happens when you do measurements. If you make measurements that are very coarse, one line segment that covers this whole set of curves, then you're reducing the distance across that measurement in comparison to what the real measurement of the river is, which is making a bunch of curves. So keep that in mind. We'll see that again, that your measurement, your effort in the measurement depends on how far zoomed in you are and how good the quality of the map you're using is. Then we get to intersections. And again, this is just a geographic feature. And what we would like to do, as always, is to see if we can treat it as a shape. So we zoom way in to this example in the image that's on the upper right. And we find that, yes, on Google Maps with a satellite image, we can actually see the bridge over the river. We can see how wide it is and we can see how long it is, which means we can put a center in the middle of the bridge where it crosses the river and draw a geographic radial to the corner. That's what we mean by treating it as a shape. If we don't have that luxury, if the widths of the paths aren't evident, again, we'll use buffers. And for the example of a bridge, remember that we had those feature types where no extent was given, something like a spring. Well, on that list of feature types, there were roads and values or numbers to use for how wide a road should be, depending on how many lanes it has. So you could use those numbers to fill in this buffer width. And the buffer would basically then allow you to estimate a shape, and then you could use the shape to create the center and radius for it, this kind of intersection. The next is a confluence. Again, geographic feature only, no changes in calculation parameters. Again, we want to treat it as a shape if we can. If we can zoom in to see where all three parts of the river segments are, then we can draw the triangle that crosses from where this river connects with the other river and where this river connects with the combined two rivers, and then the triangle, the third side of the triangle to close those two. Again, same thing. If we don't know how wide the rivers are, we have to use buffers. And to draw this triangle, the trick is to draw from where the two connect, right here at this point, the two rivers connect, find the elevation right there. And then that elevation, you're going to find on this side, and you're going to find on this side as well, somewhere. And it's that line that defines where the two things meet, because it's at that elevation that the waters mix. They can't mix until they reach the same elevation. That's how we define the confluence. Headwaters are two different possibilities for interpretation. One is that a headwater can begin at a lake. For example, the headwaters of the Nile, which begin at Lake Victoria. So the entrance of that Nile River at Lake Victoria is what the example we're showing here would be, where there's a line where the river starts and above that is the lake. In that case, it's easy. We draw the center of the river at that point and draw the radial to the two sides of the river. Simple. That's the first case, if the headwater begins in a water body. If not, there are cases where a river actually begins in a great big watershed, somewhere in upper elevations. It might be mountains, it might be hills. It's somewhere the higher elevations, and might be lots of little streams coming together and joining and finally forming the river, where the river is actually named. So in that case, a headwater might be the entire basin, the entire part of the landscape where those waters are collecting from. If that's the case, then what we need to do is draw that entire basin as a feature, call that the headwaters, and make the corrected center based on that shape, and make sure that the actual point falls on water, because it's a headwater. The type of feature is a headwater, it's not the land. Okay, still in geographic features, but now we get to the case where it's a little bit ambiguous because it just says near some feature. We've seen this in the locality types before. What we do is we try to draw a buffer around it. Now, if you think about it, there is no defensible distance that buffer should be. I can't tell you it must be 10 meters. I can't tell you it must be 1 kilometer. I can't defend that. What I can do is say, I'm going to use 10 meters, and I document that in georeference remarks. So I'm going to put a buffer that what to me means near for this situation. And what it does is it expands the shape of the feature that's mentioned just by the size of that buffer. And then we use the outside boundary of that expanded buffered feature as our new feature, find its corrected center and its radial. So again, that is going to have to be documented in georeference remarks whenever you decide what near means. The next one is interesting. It's a geographic feature only, but it's based on two features. So why is it still a geographic feature only? Because the feature is the part that's between the two features. It's all the things that are in the middle. It's not these two features themselves. It's all the things that are in the middle. Our calculation parameters haven't changed, but what we need to do is to figure out what means between those two things. And the way we do that is we find the shapes and centers of the two features that are mentioned. So here's one in the lower left that's slightly bigger. Here's its corrected center. And we go up to this littler feature in the upper right. We draw its polygon. We find its corrected center. Okay, so now we have 2 points to draw a line segment between, from the center of one feature to the center of other. And the distance between those two, the point between those two, C, is our corrected center for what it means to be between the two. And the distance D is everything that connects between one feature and the other. In other words, it's the distance, half the distance of the line segment that connects the two. So that one ends up being fairly straightforward. Now, we have the more complex situation, geographic feature only. Again, 2 things, 2 paths, and being between them. So instead of being between 2 towns, for example, it's being between, for example, a river and a road. And that relationship can be complicated, as in the illustration at the upper right. So in that case, we have a river that crosses the road 2 times. Our area of interest is in between that dotted line here and the edge of the circle here. So the river crosses the road 2 times, and the area of interest between the two is some shape here, some bigger shape here, and some smaller shape here again. So it's a piece of geometry with 3 parts. We can still do corrected centers by treating all 3 parts as one geometry and finding the maximum distance between any 2 points in any of the 3 parts. Do that if it falls in any of the parts that mean between the 2 features, we're great. Corrected center is already there. If not, we'll still need to move it onto a border to make the corrected center, and then draw a radial to the furthest point that's on the boundary of those intersections between the 2 features. Okay, so slightly more complicated. Then we get to the first of our offsets. This is not a geographic feature only calculation type, but it's an offset only, distance only calculation type. The interesting thing here is that the calculation actually ends up being exactly the same as if it were a feature. In fact, the feature type ends up being exactly as if it were near a feature locality type. But in this case, we don't have to make a guess about how big that buffer should be because we've been told. The example would be 1 kilometer from this national park. And so in this case, the 1 kilometer from the national park gives us a buffer size that we can draw around the national park. And that gives us a feature, just like in any other geographic feature only case, to make the georeference based on. We have the luxury of being given the buffer size. Okay. Then we have the type of locality that gives only a heading. It gives a direction, but it doesn't say how far. So we don't have a buffer to use. We do have a direction to go, and we have to figure out how far to go. Sometimes we have a limiting boundary. So an example would be 5 kilometers east of this feature that's drawn on the map within a particular region. And this is the region boundary. Sorry, I said 5 kilometers east, didn't I? I don't have the 5 kilometers here. I have only east of. So in this case, I go to the east until I reach that other boundary that limits me, the region that's in the locality description. It's not in the most specific part of the locality description, but it helps me to find a limit. And so I could use that limit to say, I won't go any farther than that to the east, because otherwise I'm not actually fulfilling the conditions that are described in the full location. If I don't have that luxury, I need to find out that limit to the east by making a judgment about if I go further to the east, it would be some other feature, and I wouldn't be using this one as my reference. So halfway to the next feature in that direction would be my limit. So what I need to do then is I have to delimit the angles that describe the place that I drawing the boundary around. And I use that as the limits, my geometry, my shape for the extended feature that I need to find the corrected center of. And how far or where do I start? I start in the the corrected center of the feature that's named. So I start at A, I go east until I find the limit. I have to say why I have that limit. Either it's because of a region that's been named or because it's halfway to something that's over there. Okay. Beginning to lose my voice here. Okay, the next is an offset. And now we're getting into a situation where we need to measure along line segments. Rather than having big shapes, we're going to start going on roads or rivers and things like that. In this particular case, my calculation parameters are going to be the same in the calculator, but I need to treat the part of the path that's within the reference feature as the geometry to start with. What do I mean by that? So my example, let's say that the offset is on a road to the east of a town. So I need to decide where to begin. The road begins here, inside the town, in an intersection with another road, and it goes to the east. The part of the road that's actually within the town still is this shape that's drawn around A. So that's the part of the path that's within the reference feature, within the town that's named. That's what I use as my geometry. I find its corrected center A, I find its radial B by going to the farthest corner, and that's what I use as the size of my starting feature. Now, again, if the path isn't wide, I use a buffer, same as usual. Then what I do finally is measure the distance on the path in the given direction, east, taking that final measured distance as my new corrected center. I'm going to start at the center of my first feature. I'm going to measure along the road till I get as far as it says to go, and that's my endpoint. That's my new corrected center. My radial is going to be the same. I've already figured that out, but my new center is going to be here. So that's how we calculate that one. Then there is the beast. This is the worst possible situation. It's complicated. I'm going to go through it quickly. You are very unlikely to encounter this, but I want you to see the thinking that goes by, that goes into trying to figure out very complicated feature types. So in this case, what we have is an offset along a wide path. The wide path is a very wide river, and the starting point is some town on the side of the river. That's my example here. So what do I do? First, I find the starting point, which is the corrected center of where the town and the river meet. So that would be point A1. It's the corrected center of the border between town and river. B1 is the radial from that point to the edges of the town meeting the river. So we're going to use the same calculation parameters as always so far. And what I'm going to do is I'm going to make a note of that distance B1. I'll call it U here for uncertainty, because I'm going to use that value as I go downstream to try and find out where this place really is. And I'm going to calculate the uncertainty as the locality type, a geographic feature with an obvious spatial extent. The geographic feature is this edge of the town. Okay, what do I do with that? I'm going to go from that position in the town, and I'm going to start measuring all the various ways that I can go along the wide path. One of them is this dotted line here that ends up putting me at X on the border of the river on the north. Another one is to go down through the middle of the stream here to this point X. It takes me a little bit further down the river. Another one through the islands in the middle to this X here. Another one through the channel at the south to this X here. And finally, another one along the shore to this X here. So I'm basically trying to figure out all the places that I could end up if I went a certain distance down the river. And they're occupied by all these X's. From there, what I do is I go back upstream and downstream by that uncertainty distance I calculated in the first step. So it could be a little bit upstream or a little bit downstream based on being upstream or downstream starting points here. And I do that for every X. Once I do that, I get a shape. That's what this slide is saying, basically, is that I'm going to build a shape around all the possibilities for going a distance down the wide path. And that shape is what I'm going to use as my feature. So as a shape method, this shape would be the final answer. But to turn it into a point radius method, I need to find the corrected center in the river, not on an island, because it's along the path and the path is a river. So corrected center needs to be in the river, and the distance will be the distance from that point to the furthest point in the shape that I defined by the previous method. Whew. That's a rough one. Don't take it, don't be too worried about that one. If you actually need to do it, you'll come back to the directions in the georeferencing quick reference guide for how to do that and go step by step. And with that, you'll have success. Now we get to the first of the offset types and calculation types that actually has different or added calculation parameters. Up until now, we had everything on the list down to measurement error. Now we add two things. We added distance precision, and we add distances and directions into the calculations. So the distance precision, by the terms of the georeferencing best practices, is defined by the most precise distance given. The assumption is that in the description below, the example below, that says 3 kilometers south and 4.4 kilometers east, that the person who wrote that description was aware of and measuring distances to the precision of 0.1 kilometers, even though this one, if you took it on its own, would be to the nearest kilometer. So that's how the precision comes into play. That will go into the distance precision parameter. Distance at a heading, again, the calculation parameters differ. Here, we'll still have a distance precision, everything above it the same as in geographic features only, but this time we're going to add distance and directions. Take note, we've seen this before, that the uncertainty increases with the distance from the reference feature. In other words, the further east we go in this diagram, the bigger that triangle is going to be. Then we get into the simpler stuff. The geographic coordinates only, you can see there are far fewer parameters, but they're not all the same parameters as before. We include GPS accuracy here, none of the distance and direction things. Coordinate precisions are the equivalent of having an extent when the locality is described by coordinates. And that's why an extent is not needed in the calculations. The extent is already given in the coordinate precision. So in the diagram, it says, okay, we're given that coordinate, but because of the precision, it could be anywhere from here to here or from here to here, basically giving us a box. And that's all we need for this calculation. The situation is similar whenever we have a grid system. So for UTM coordinates, that is a grid system. It's not, they're not squared. They increase in their size. They decrease in their size as you go north or south. In this case, we can treat the calculation as a geographic feature with obvious spatial extent because the obvious spatial extent is the grid square. The coordinates of a corrected center of a UTM grid can be converted to decimal degrees, and those are entered into the calculator. And the radial is just half of a diagonal of a UTM coordinate precision. And you can see there's a note here on the radial that if you multiply the width of a UTM coordinate, which might be meters or 10 meters or 100 meters or even a kilometer, that you multiply that by 0.707, and that's the radial for that type of a grid size. Then you can put it into the calculator as a geographic feature with obvious spatial extent. Then we've seen a lot of this before. We're out of the specific locality types and into specific situations where you might need to do something tricky. The first one is where some part of the description is dubious. It's in question and it says so. So the example at the bottom, everything's fine. Somalia, Puntland, Nugal are all good, but the last part of the description is in question. They're not sure if it was there. What do? We do not georeference that part. And we say so. But we can georeference all the rest of it that's not in question. It'll be way bigger than the more specific part of the locality, but it will contain that and all the other possibilities for the description. So we're going to georeference the most specific part that's not in question, which is Nugal for this one. When there are demonstrable inconsistencies, we are not going to georeference it without enough evidence to be sure what part of the description is wrong. Sometimes it's very hard to tell. Sometimes it's a good guess and you're able to do the georeference anyway, as long as you say what the assumption was. And you can georeference the most specific part of the locality that is correct. In other words, the final georeference would contain the less specific one, even if it isn't correct. And then document the features that were used and the criteria that were used. If you can't find a feature, and it's the most specific part of a locality, then you can still locate the less specific parts of the locality and georeference that and do it unambiguously, then go ahead and georeference it. If you can't figure out where the thing is at all, obviously you can't georeference it. If you have to georeference only part, you document which part was used for the description and georeference that. Okay, even if you can't georeference it, it's worth noting in your georeference sources what you used to try, because if somebody else comes along later and says, I would like to georeference this, they can see, oh, you used Google Maps, you used this gazetteer, and you used Wikipedia, you used Google searches, and you couldn't find it with any of those things. That might help them to narrow down other resources to use to try to find the place. If you have multiple possibilities, doing the calculations depends on what you have, what possibilities you have. Sometimes you can treat the feature as a combination of all the candidate features. So Paula gave an example of something nearby here where there's a feature whose name can refer to a lake and to a town and to a national park. In that case, you could do the georeference that includes all three of those things. If the things aren't related to each other, then you aren't going to want to do the georeference, just as we said before. Unrelated features, far distant from each other, shouldn't be georeferenced. It is possible that if you use a combination of features, you're going to have to correct a center so that falls on the boundary of one of those features, the one that's boundary is closest to the center that you've figured out. And again, document the features that were used. Finally, there is no problem with georeferencing locations that happen to be for cultivated or captive species, because we can capture the information about the fact that they're cultivated or captive in the Darwin Core term establishment means. The georeference is still valid. Somebody might still be able to use it. And so we don't refrain from providing those georeferences. Summarizing, we know that boundaries and paths can change over time. So that ideally, if we know the date of a location, we could georeference it with the maps from that period. We aren't going to have that luxury in this project, but keep in mind that that's the case. Also note that paths can be very sinuous. They can have lots of curves in them, change directions a lot of times. And that as you measure along such paths, you are accumulating error on the final position by not being very precise about where you draw the lines. The fewer lines you draw, the more error you're going to accumulate. If a coordinate source is a GPS, the GPS accuracy at the time the coordinates were taken is what we want as our measurement error. Sometimes we don't have that and we have to provide a default value. And whenever there's an ambiguous adverb of place, such as near, around, in the vicinity of, those we don't consider to have any particular meaning other than near and doing the calculation the way we do near. Final considerations, we always want to report our assumptions, considerations, exceptions to the protocol. We always want to report our sources and to the most specific extent possible, including things like the year of publication. We want to try to use any additional information that we can find to reduce our uncertainties wherever possible. And remember, it's better to overestimate uncertainty than to underestimate it. By underestimating, we could be wrong. By overestimating, we aren't wrong. We're just bigger than we might be if we had better information. And then use the georeferencing metadata like the protocol, the sources, and the remarks to make sure that your georeference is reproducible. So that's it. That was an intensive, very long presentation on how to do specific kinds of georeferences based on locality types using the point radius method and talking about the parameters that are going to go into the georeferencing calculator. So we have about a half an hour to look at the calculator. I'm going to switch over to the presentation that's very brief on the georeferencing calculator itself, and then get into the calculator. So here we begin again. This is a separate presentation in the resources for the course. And this one is for the georeferencing calculator. It's just a quick introduction. So remember in the last presentation, we saw what the point radius method consists of, the steps that have to be taken. And they are these 7. So a lot of that we're going to have to do on maps and measuring things. And then finally, the georeferencing calculator is to simplify step 6, to calculate the final center and uncertainty using a tool. So remember that the calculations depend on the type of locality and the values of the uncertainties that go into calculating for that specific locality type. In terms of the calculator, it means what parameters do we need to enter into the calculator to make sure it makes the right calculation. And the georeferencing calculator is the tool that does the point radius calculations for you for one-on-one single georeferencing situations. This is what the calculator looks like. We already talked about these sources in the previous presentation. So we're going to just talk about the fact of where these things end up. The calculations for the point go into decimal latitude and longitude. The information about the coordinate reference system or datum goes into geodetic datum in Darwin Core, and the final uncertainty distance goes into the coordinate uncertainty meters. And now we're going to actually switch over and look at the calculator in progress. I need to stop sharing that for just a moment. Go over to my georeferencing calculator, come back and share again. And I would like to know if that georeferencing calculator is basically filling your page. Okay, I've refreshed it. Just quickly, Paula will give you the link to the georeferencing calculator. The georeferencing calculator runs in a browser. That doesn't mean you have to be connected to the internet to use it. You can connect to the internet to open the calculator, leave it open, and it will run perfectly happily until you close your browser. Also, there is a version of the calculator you can download to your desktop, And when you open it, it's going to open in a browser anyway, just like this does. It's exactly the same. But you could open it even if you weren't connected to the internet, because everything is stored locally. So that's the basics of the georeferencing calculator. Now, when you open the georeferencing calculator, it looks like this. There's not much there. You can choose a language from amongst these. And when you do, all of the labels change. All of the help items change to that language. We're going to be doing it in English today. At the bottom, there are some tools, and these are to make conversions, but they're not about doing the calculation itself. The calculator doesn't let you do anything until you pick the locality type. So let's go with the example of the locality type that we had at the beginning of the point radius method presentation, which was a offset at a heading or distance at a heading. That's this last selection on the georeferencing calculator. Once I make that selection, the calculator fills with all of the fields that you need to fill. Basically, everything with a white background below the locality type are the fields you need to fill. After that are buttons to actually do the calculations, and below that are the results of the calculations. That's it for the calculator. So it makes things easy in that only thing you need to do first is decide your locality type. Once you have that, you need to go and fill in all the parts. So let's think about that example from the first presentation for today, which was the point radius method presentation. Our example was 4 kilometers southeast of Ikusu Island. Now, in the presentation, it didn't show us where we got the outline of the island, nor where we figured out the corrected center from. But let's assume that we use Google Earth to do that. On the list of coordinate sources is a whole set of maps, plus GPSs, plus Gazetteer. In this case, what I used was a Google Earth, and the maps that were being used in Google Earth were newer than 2008. So I make that selection in the coordinate source field. Why does that matter? Every one of these choices affects the uncertainty of the coordinate source. Google Maps, with maps later than 2008, has a specific error associated with it. They're not perfect. Before 2008, there was a different error, and it was less perfect than after 2008. So we need to choose our source correctly. We got our coordinates from Google Earth, and they were to many, many, many decimal places in decimal degrees. So I need to make sure that I select decimal degrees as my coordinate format. If I happen to get them from another source in a different format, for example, in degrees, minutes, seconds, I need to select that. And when I do, the input latitude and longitude fields change, and it's kind of hidden, but also the precision values change. They allow for nearest minutes, nearest seconds, etc. Whereas if I have my coordinate format as decimal degrees, I can only enter decimal latitude and longitude, and my precisions for those coordinates are measured in degrees. So the calculator is making adjustments as you go, starting at the top and just following down. So I'm not going to go and look for the actual coordinates of the island right now, just so that we can do this, this demonstration. So suppose that's the number for the latitude that I got on Google Maps, and this is the number I got for longitude, sorry, from Google Earth. And Google Earth is using WGS84. So I can select WGS84 for my datum. Remember, I'm just basically following the recipe, filling in things from top to bottom as I go. Because I chose decimal degrees, I can now select my coordinate precision. I took all the coordinate precision that Google Earth could give me, and that's more precise even than this 5 decimal places of decimal degrees. So I need to choose exact. my precision is essentially exact. It's not going to contribute any error because there's so many decimal places. So I finish with the first column. I start with the next column. My description was 4 kilometers southeast of the island, if I remember correctly. So my direction is southeast. I need to select it. You'll notice once I selected it, a box went away here. Something is no longer relevant. It's because I started with this option, degrees from north. If my direction was measured in degrees from north, I'd need to put a number in here, but it's not. My direction is southeast. So that box goes away. Thank you, calculator. Now, we had a distance. Our offset distance was 4, and the units were kilometers. I need to make sure that my number matches my units. Having done so, I need to make sure that all of the other boxes that I need to fill are also based on kilometers. So I'm going to make up a radial for that island, and I'm going to say that it was 3.4 kilometers. My measurement error is my capacity, my personal capacity to measure distances on Google Earth. So I was very careful. I went in, I zoomed in as far as I could to make sure that the ends of my points were on the farthest distances of the island. But I know that even doing that, I usually make a measurable error of 5 meters. I need to convert my 5 meters to kilometers. So what is that? It should be 5 thousandths of a meter. That's 5 meters in kilometers. Now, what was the precision of the original description? If it was 4 kilometers, then my precision is to the nearest kilometer. I need to choose the precision. I've filled in the georeferencing calculator completely. All the fields are filled. I've done what I need to do for this calculation. All I need to do is click on calculate. We've got a microphone open. Okay, so I've clicked on calculate, and the answer comes up. You can see that all of the fields down below here have been filled in. My datum was filled in from the choice that I made. The latitude and longitude, you can see that they're not the same as the starting point. That's because I went 4 kilometers southeast. So the end points are not the same as the starting points. That's good. The final uncertainty calculated by the calculator was 4,486 meters. Remember, this is a coordinate uncertainty in meters, so it's ready to go. It also filled in automatically for me the precision of the end product, which was to 7 decimal places. It filled in automatically the date it was done. This is the georeference date. I can fill in my name here. Why would I do that? Because if I select all these other metadata, in my case, I used the newer version of the Georeferencing Quick Reference Guide, which has Paula as the first author. Now I've got all the information I need to fill in a spreadsheet. What I do then is I copy, and it says here that it copied these values with tabs in between each one that can now be pasted directly into a spreadsheet. I'm going to demonstrate that to you very quickly. I've got a spreadsheet here I could stick it into. Ignore what's in there before. Now I'm going to just select this particular position and paste. And you can see I've got decimal latitude, decimal longitude, geodetic datum, coordinate uncertainty in meters, coordinate precision, georeferenced by, georeferenced date, georeference protocol, all of it filled in with one paste from the georeferencing calculator. So that's the basics of how you're going to want to use the calculator most often. The 2 converters at the bottom will be useful to you. For example, if you don't have an easy way to change the distance that was given in the locality description into the units that they need to be. For example, if I need to do a calculation that says how far is 1 kilometer, I've chosen 1 for my start value, kilometer for my start unit, and I choose that it needs to be in meters when I'm done. Okay, 1 kilometer is 1,000 meters. That was an easy one. There are other ones that aren't so easy. I've got the option for miles. Not so easy. I've got the option for yards. I've got the option for feet. And the third one you may not recognize is an option for nautical miles. So these are all ways to make sure that the values that go in for distances and radials and measurements here can be converted into the units that you were forced to use because of the locality description. That's how the distance converter can be used. The scale converter is nice because it can tell you, suppose I have a map where 1 centimeter has a scale of 1 to 20,000. How many kilometers is 1 centimeter on that map? Well, it's 0.2 kilometers. If I multiply that by 10, my 10 centimeters on the map should be 2 kilometers. So these are additional parts of the calculator application. They're not connected to anything at the top, but they allow you to provide values that could go into the fields at the top. So I've showed you everything on the calculator for this particular locality type, except one thing, which is this Go Here button. That one is not going to be relevant for our purposes, so I'm going to skip it here. If you're curious what this is about, and it is curious, you should go to the Georeferencing Calculator manual and see what that does. The last thing I want to show here is, okay, I've done my georeference. I've entered my answer into a spreadsheet. I'm super happy. I need to go on to my next georeference. Turns out my next georeference isn't a distance at a heading at all. It's a distance along orthogonal directions. So I need to change my locality type. When I do, bam, the values that were in the calculator before remain, except where there's some new parameter that needs to be used. So the difference between distance at a heading and distance along orthogonal directions is that the distance along orthogonal directions has 2 directions in it. It has east-west plus north-south, as opposed to, in the previous one, if I go back there, only one direction, which could be any of those possibilities. Okay, so back to orthogonal directions. How do I proceed? I fill in from starting at the beginning and going all the way down the first column, then going all the way down the second column, filling in everything as appropriate. When I'm done with that and I'm confident I've entered everything correctly, I click on Calculate. The one other thing to mention here is that you can see that all the previous values were kept. This is very useful to not have to enter parameters that remain the same between one locality and the next. So if my locality for the first calculation I did with distance at a heading started at Ikusu Island, and this one also starts at Ikusu Island, and I use Google Maps, then everything in this first column is the same. I don't need to change any of it. It's all ready to go. These are the decimal degrees from Google Earth for the WGS84 coordinate reference system with exact precision. All the same. All I really need to do is to change the north set offset. Suppose it's 5, our units are kilometers, and to the south. And instead of going 4 kilometers in the other direction, I'm going 3 kilometers to the west. Our radial is still the same radial as the island. Don't need to change that. My measurement capacity is still as bad as it was before. My units are kilometers. My precision's still kilometers. not anything more specific or less specific than a kilometer. Precisions are here. I calculate, I have my new georeference. You might remember that in the previous answer, the coordinate uncertainty in meters was 4,400 and some. This one's less. It's less because we've removed some uncertainty from direction precision, which we saw in the previous presentation. The point to take from that is you can use this calculator and play around with the values, increase the distances to east or west, change the offset directions, change the precisions, and see what effect it has on uncertainty. You can study how the various aspects of the locality description affect the uncertainty. Let's do one quick one. Suppose we didn't know that the datum was WGS84, that it was not recorded. Nothing else changed. I do a new calculation. Oof. Instead of being 4,100 meters, I've jumped up by 5 kilometers. My uncertainty is now almost 10 kilometers because the datum was unknown. That's to underline the importance of datum. So that was a quick tour of the georeferencing calculator. You're going to be using this a lot, and there are exercises in the modules for today that will use the calculator. And we'll have an opportunity to cover any questions that might arise on Friday for this. I'll stop sharing. I'll see if there are any questions and see after that if there's anything else that Paula would like to add. Okay, so I see Paula's added the references. Okay, there is a request to explain again the determined radial of a feature and measurement error. I'll start with measurement error. Measurement error is my personal capacity to measure things on a map. So I might measure a feature, a radial of a feature on a map. I come up with a number. That's my determined radial distance. I'm going to say that that number is good to within my measurement error. So I add my capacity to make that radial in the measurement error. The measurement error is going to go into the calculation as a separate item. The radial is going to be fixed. So basically is what the combination of these two things is. I measure a radial, that goes into the calculator. I tell them a measurement uncertainty, and that's going to tell the calculator, based on my measurement of that radial, you might need to go in 5 meters or out 5 meters. The final calculation needs to accommodate my capacity to measure on the map to within 5 meters. That's the number that I gave for me based on experience. Yours might be different, but it's not a bad number to use. Does that help explain the difference between that radial and the measurement error? I hope so. If not, let me know. I'll go on to the next question, and that is, will we have the same locality types for all examples? I'm not sure I understand the context for the question. We have the exercises for this module, and we will have lots of different locality types. So they won't all be the same for the exercises. When the time comes for you to do real world georeferencing, you're going to get whatever. All of these things might be encountered. More often than not, we found that about 45% of all locality descriptions, their most specific part is a feature only of one type or another. After that, the most common is a distance at a heading. And after that, orthogonal distances. And after that, there are others that come into play, but we're talking about maybe 4 or 5% of the time versus the 45% that the geographic feature only ones will appear. I hope that answers that question. If not, let me know and I can elaborate on either one of those questions. And any others? If not, we have about 10 minutes. Paola, did you want to say anything more in particular? If not, I can use those 10 minutes for a real demonstration of the calculator with that example from their first presentation.
I think you can go ahead and explain that example. At the very end, I want to make some comments to take into account for the next sessions, but for now, just go ahead with the example.
Okay, I think this might be fun and useful. So let's first share the screen again. Let's go back to the example from that first presentation. So remember that, let's go all the way to the beginning of the description, which was this one. So we've already decided that the most specific part of the location description was 4 kilometers southeast of Ikusa Island. We determined that that was a distance at a heading. That's what we did when we used the calculator, and our feature is Ikusa Island. That was the outline of it, at least on the presentation. And somewhere down here, it told us what to do with that outline. Here's the boundary. It says, okay, let's make this measurement of the most distant 2 points on the island. Now I need to switch over to a tool. I'm going to use Google Earth for this. Here's the island in a satellite view. And what I want to do here is to make a measurement, if I can. I've got this thing in my way. Okay, now it's out of my way. I want to make a measurement. I'm going to do it with a line. And I'm going to start my line up here at what I think is one of the most distant points. Then I'm going to draw to what I think is the other most distant point, which is down here. So here I've drawn that line, which should be comparable to this line in the presentation. And the center of that line is going to be the point A from the presentation. And I can see that the distance was 9,282 meters from there to there. Is that really the farthest distance along anywhere on the island? Well, I'm going to try just to adjust that and see if by chance this point down here was further. So now I've moved that line and look, it's 9,114 meters. Okay, so that's less. I guessed correctly. My intuition and my eyeballs were good, and that was the distance. So let's have a look at my measurement error. I just drew these lines being zoomed out far enough to see the whole island. Let's see how well I did at actually getting to the edge of the island. Oof, I did not expect that. It's on the edge of the island, but it's not the most distant point. So I would have to move that over here to be the farthest away in that direction. Now, let's zoom back out and see what happened on the other side of that line. So let's zoom back in. Oop, no. Sorry. I clicked and I shouldn't have clicked. Sorry. I need to start that again. Very sorry. I won't repeat that. I'll draw my line quickly. But you can see how I would adjust my endpoints and try to make sure that the distance was as good as it could be. Again, there's my line. The center point would be the midpoint of that line. Now, I'm very far away from being on the island in this center point. So what I need to do is to move my center point somewhere in the direction of the island. I'm not going to do it exactly the way that I did before. What I'm going to do is I'm going to draw a circle that begins at what was basically my midpoint to the edges of the island in both sides. Okay, so I need to adjust my circle. You can see how I'm drawing it. It's too far to this side because I'm beyond the circle. So I'm going to adjust my center. I'm going to adjust my radius, adjust my center. Each time trying to get closer and closer to the midpoint so the circle intersects both edges. So I'm getting pretty close now. So that's that circle from the first image. Now, remember that isn't falling on the island, so I need to make a corrected center. So what I'm going to do is I'm going to move my circle so that it touches the island. I'm going to slip it down this way. And I'm going to put it on the spot on the border, on the shore of the island that makes the distances outside of my circle be the same on both edges. So here's my distance on this side. I'm just doing this by eyeball. Here's the distance on this side. So, okay, I'm going to say that's more or less correct. So I've done this step to create this dashed line. I've got my center, corrected center on the island. What's next? Next is to increase my radius so that it covers both of the farthest points. Switch back here. I'm going to now increase my radius of my circle so that it covers this edge here and this edge here. See what I've done? I've increased my circle to cover those two spots. Okay, that's my corrected center and radial. My radial is given in this box. It says that it's 5.3 at 5,322 meters or 5.322 or 323 kilometers. That number I want for my calculator. Let's go to my calculator. So here, distance at a heading, Google Earth was my source, decimal degrees are my source. I don't have these numbers yet. I'm going to get them in a minute. Our description was southeast, I believe. Checking. I just want to make sure. The direction was southeast, yes, 4 kilometers southeast. Go back to my calculator. My offset distance was 4. My direction was southeast. Okay, I have those two things in there, but my radial was the thing that I just measured. Go back to Google Earth. My radial was 5.323 kilometers. 5.323 kilometers. Remember, I had to change it to kilometers because my offset distance is in kilometers. My measurement error, I'm going to keep at 5 meters. My distance precision really is 1 kilometer because it said 4 kilometers. My datum is known. It's Google Earth and it's WGS 84. What I need now are the actual coordinates of my corrected center. I don't have those here yet. Let's go back to Google Earth. My corrected center is way in there. You can see that I actually was a little bit off from the coast. I need to move that to the coast. And to get my corrected center, I have a tool here that lets me put a marker. So I can slide my marker to the point that was the center, put the crosshairs on the center. And here are my coordinates, which I can copy from here over to the calculator. That was my latitude. This one's my longitude. I want to keep this sign because I'm in the southern hemisphere in Tanzania. Those are my coordinates. My precision was 1, 2, 3, 4, 5, 6 decimal places, which is better than any of the other selections here. So I'm really in the exact realm. I do a final check. Distance at a heading. Yes, it was 4 kilometers southeast of a thing. Google Map Earth is my source. It's from a layer. Let's check that. My map is actually from 2023. Good. So my map layer is greater than 2008. I'm in decimal degrees. Those are the values I copied from Google Earth, which is in WGS 84, exact precision, southeast direction, 4 kilometers. My radial was 5,323 meters. That's what that is in kilometers. My error is 5 meters or 0.005 kilometers. My distance precision was 1 kilometer. Everything looks right. I calculate. That's the real answer for the georeference for our example from the first presentation for 4 kilometers southeast of Ikusa Island. So there we've done an entire real demonstration with a real locality, getting a real georeference. So I'm going to switch off here now. You'll have this to refer back to in the recording. And let's see if there are any other questions and or closing remarks from Paula. Okay, the first question came up after saying the tool that I just used to measure the radius, is it Google Earth? Yes, that was Google Earth. I used nothing special except Google Earth. And you can see why Paula likes that one. It's got nice tools. And Paula answered that below. Okay, I'll switch it over, let Paula take it away.
Okay, thanks, John, very much for the presentations for today. Are there questions from the participants? Remember, you can open up your microphones if you prefer, or you can write them on the chat. I don't see any coming yet, and so I'm going to stop the recording now, but we will remain here for a couple of minutes more.